Hello everyone, my name is James Ryan, and today I'm here to talk to you about curved paths for robotic motion and the idea for a new algorithm and program that I'm going to create in the future. In this video, we're going to be talking about the motivation and concepts behind the program and the algorithm. In the future, I'll make a video where I create it, and maybe after I figure out any problems with the program and fix those, I'll do a follow-up video explaining further. So I've been thinking about algorithms for robotic motion, and I realized that I need some good paths for the robots to follow. While some of my future algorithms will involve a robot perhaps planning a path on the fly, or the direct application of differential equations to the robot, or even a combination of both, this program has one simple task: turn jagged polygonal paths into smoother, rounder paths that a robot can follow more easily. This algorithm will be the first in my series of robotic motion / path algorithms, so I want to make it as simple as possible as a base for more complicated projects. The simplest version of this assumes that the robot is going as fast as possible, never slowing down to turn. We also assume that the robot has a finite acceleration, so it can only change direction so quickly. Otherwise, the path wouldn't need any curves at all, and the algorithm has nothing to work with. Some simple maths will show us how big our curve radius will need to be. First, we have the formula for tangential acceleration in uniform circular motion and our constraints. As you can see in the diagram, when an object is undergoing uniform circular motion, there is an acceleration towards the center of the circle equal to the velocity squared divided by the radius. Now, our constraints that we need to plug into this formula is that our velocity is always our maximum velocity, Vmax, and our acceleration is going to be less than or equal to our maximum acceleration. We don't want to exceed that. Plugging those two equations into the original formula gives us that the maximum velocity squared divided by the radius of the circle is less than or equal to the maximum acceleration, which therefore means that we have a minimum radius, r, which is going to be greater than or equal to v squared over a, or the maximum velocity squared divided by the maximum acceleration. This gives us the minimum radius of the circles we'll use. So in the algorithm, the radius of the circles we use have to be either this size or greater. So, how are we going to do this? I'm going to use a Rewrap algorithm. We assume that the robot is either traveling in a straight line or is turning in a circle. If we look at the diagram I drew earlier, part of our algorithm becomes clear. We need to replace the points of our path with circles. Then we need to rewrap our path around these circles, like so. Now the algorithm follows now the robot will follow curved paths. Note though that now the path curves around the points instead of going through them. Obviously this is a problem, but it's easy to fix. If we modify the original path slightly before applying the rewrap algorithm, we can ensure that the circles curving around the modified path will pass through the original points, like so, as shown in this diagram. Although one of the circles is a bit wonky because I didn't really think about this when I was drawing the diagram, but still the same. And this is the same picture, but with those lines removed, so you can see the now smooth path passing through those original points. A good method for taking intuitive ideas and making them into algorithms can perhaps be summarized by a simple process. We start with a goal, we move to an abstract concept, we move to a more concrete concept, which then becomes a geometric algorithm, an algebraic algorithm, and then finally we can code it. We've already made it about a third of the way. Our goal was to create curved paths for robots to follow. So we turned that into an abstract concept, where we would take polygonal paths and curve them. This became a concrete concept, where we said we would replace the points with circles we would modify those circles' positions so that they coincided with the original points, and then we would rewrap the path around those circles. The next thing to do is to turn that into a geometric algorithm. This means using terms like tangents, dot products, vectors, other things, so we can turn our rewrap algorithm into something mathematically even more mathematically concrete, something that we can actually tell a computer to do. Then we'll need to turn our geometric algorithm, which is great if you have some geometric software that can do that for you, but not so great if you're coding it yourself. You need something that a computer can actually do. A computer doesn't understand circle or line, but it can do the maths behind the circle or line. So we turn it into an algebraic algorithm. Finally, once we have our algebraic algorithm, we need to turn it into actual code that the computer can read. Everything up until now has been either a concept or pseudocode. Obviously, you don't always follow this process. Sometimes you have to go back up the ladder to go back down, and this is more of a general concretization of ideas as you go through the creation of software and the software creation process. And obviously it will be different for different types of algorithms. Not all algorithms will be geometric. Sometimes they'll be more about probability or combinatorics, for example. But a lot of them are. So, we've already made it about a third of the way. One thing to keep in mind as we progress is to keep our higher level ideas in mind, especially the connection between geometry and algebra. Algebra and geometry are deeply connected, and true insight lies in the connections between them, understanding the connections between them. Because they are two sides of the same coin. In fact, we'll make extensive use of their connections in making this algorithm and in future projects as well. Next week, on Experimental or Cerebral Explosion, I don't know if I changed the channel name yet, we'll be using tangents, squared distances, dot products, cross products, Newton's method, and vector division. Tune in next week to find out how all this combined can solve the problem and save the day. Or not.